In this screencast, we're going to examine the effect of a heated plate on the velocity profile and the temperature of a relatively cool fluid flowing down its length. Let's begin by defining our coordinate axes. X will be in the direction of flow. At x equals 0, we've got the leading edge of the plate. Y will be the vertical direction, the distance above the plate itself, and Z will be a direction orthogonal to both of these. Now let's make the assumption that the plate is relatively wide compared to the flow direction, so we don't really need a z direction. The plate's going to be so wide in that direction. So ultimately this is going to be a two-dimensional problem. We'll be looking at a number of different fluids in this screencast, but in all cases the speed of the fluid far away from the plate is going to be u infinity, and we'll set that equal to 0.05 meters per second. The temperature of this fluid far away from the plate we'll call T infinity, and we'll set that to 0 degrees C. And we're also going to say the temperature of the plate, the temperature at the surface, is going to be 100 degrees C. We'll call the length of our plate L, and we'll set that equal to 1 meter. What we're going to explore are a number of graphs in which we've got y on the vertical axis, x on the horizontal axis. I'm showing the plate down here. This again has a surface temperature we'll set at 100 degrees C. At a distance far away from it, we'll set T infinity is equal to 0 degrees C. And the vertical axes are going to range arbitrarily from 0 to 0.1 meters. Do keep in mind that that dimension goes up to infinity. And on this part of the graph, we've got x equals 0, which represents the leading edge of the plate, and I've got x equals 1 meter, which represents the trailing edge of the plate. And when we show these simulations, we'll have a color scale on the right that goes from the surface temperature of 100 degrees C down to T infinity, 0 degrees C. Some of the other trends that we're going to see is the momentum boundary layer, and I'm going to use a dashed line for the momentum boundary layer. It'll be more obvious when I show the graphs, but recall from fluid mechanics that the boundary layer, the definition of the boundary layer, is a location where u, the horizontal component of the fluid velocity, is equal to 99% of u infinity. So in our case, 99% of 0.05 meters per second is equal to 0.0495 meters per second. So when you see these dashed lines, just know that the horizontal component of velocity is equal to 0.0495 meters per second. The thickness of the momentum boundary layer we'll denote with the lowercase delta, and that's a function of x. So we'll find that the thickness of the momentum boundary layer at the leading edge of the plate is much smaller than the thickness of the momentum boundary layer downstream. Another thing you're going to see is a solid line, which we'll call the thermal boundary layer. The definition of the thermal boundary layer is that the temperature anywhere on this solid line is equal to 99% of T infinity plus 1% of the surface temperature. So in our case, with the surface temperature of 100 degrees C, T infinity of 0 degrees C, we'll find that the temperature everywhere on the thermal boundary layer is going to be equal to 1 degree C. We're going to define the thickness of our thermal boundary layer with the Greek letter, again, delta with a subscript T to represent temperature, and that's also a function of x. And the thermal boundary layer is thinner at the leading edge of the plate, and it gets larger as we move downstream. So to reiterate, the solid line, everywhere on the solid line the temperature is equal to 1 degree C, and everywhere on the dashed line the speed of the fluid will be equal to 0.0495 meters per second. So a couple of parameters that we need to define, the first of which is the Reynolds number, which we'll define as rho times u infinity times some length scale. And now the length scale I'm going to use is the x-coordinate, so the distance from the leading edge of the plate divided by the dynamic viscosity. To figure out what the length scale is, a method of notation is to use a subscript x, just to denote that x is the length scale. And by the definition of our kinematic viscosity, this is just equal to u infinity times x divided by the kinematic viscosity. Note that when we defined it this way, the Reynolds number is a function of x. At the leading edge of the plate, the Reynolds number is going to be equal to 0. So at this dashed line, the Reynolds number is equal to 0. As we move down the length of the plate, as x gets larger, everywhere on this dashed line, the Reynolds number is continuously increasing. And it's increasing in proportion to the distance at which we've moved downstream of the plate. As we continue all the way down, at the end of the plate will be at a value of x equals L. And we're going to define this one now, the length scale. We're going to use RE sub L to define the length scale. And that's going to be equal to u infinity times L divided by the kinematic viscosity. So the highest Reynolds number we're going to see in this scenario will occur at the end of the plate. So let's back up a second. One thing that we need to confirm is that there's no region on the plate in which the Reynolds number is greater than 500,000. Because if that's the case, if this was at 500,000, for example, we would find laminar flow upstream of that dashed line, and that laminar flow will turn into turbulent flow once Re sub x exceeds 500,000. And this type of flow we can't handle mathematically the way we're going to look at these simulations. So we're just going to confirm that the Reynolds number Re sub L is less than 500,000. So that's a major assumption that we're making, is that the flow is laminar. Another dimensionless quantity we need to define is known as the Prandtl number. And the Prandtl number is the ratio of the kinematic viscosity divided by the thermal diffusivity. So fluids that tend to have a low viscosity and a high conductivity would tend to have relatively low Prandtl numbers. Something like this might be mercury, for example. On the other end of the spectrum, fluids with a high kinematic viscosity and a low thermal diffusivity will tend to have very large Prandtl numbers. An example on this extreme would be something like motor oil or olive oil, for example. What we're going to observe is that the Prandtl number will affect the relative thickness of the thermal and the momentum boundary layers, such that a Prandtl number smaller than 1 will find that the momentum boundary layer will be thinner than the thermal boundary layer. A fluid that had a Prandtl number of 1 will find that the two boundary layers are going to have the same thickness. And then for Prandtl numbers greater than 1, we'll find that the momentum boundary layer is thicker than the thermal boundary layer. We'll also find that the thickness of the momentum boundary layer is a strong function of the Reynolds number, such that a very large Reynolds number will result in a thin momentum boundary layer, so small value of delta. A large Reynolds number would be, in our case, will be a fluid with a small viscosity. These are the four fluids that we'll be looking at. I've provided Prandtl numbers, kinematic viscosity, and the Reynolds number at the trailing edge of the plate. Note that we'll be working with air, water, mercury, and oil. We'll have Reynolds numbers that range from over 400,000 down to about 50 between mercury and oil. And the Prandtl numbers are going to range several orders of magnitude between something really small for mercury and something really large for oil. So do keep in mind how they will impact the relative thickness of the thermal and momentum boundary layers. And because we're holding the speed of the fluid and the length of the plates constant, we'll find that the Reynolds number scales with the kinematic viscosity. Fluids with a very large kinematic viscosity will have small Reynolds numbers like oil. Conversely, fluids with small kinematic viscosity will exhibit a large Reynolds number. So let's take a look at our first simulation, which is air. If we zoom in on it, what's immediately apparent are the velocity profiles. They start out at U infinity, and right when they hit the momentum boundary layer, which is the dashed line, the velocity is 99% of that free stream velocity. And then, due to the no slip condition, the velocity goes to 0 at the surface of the plate. As we move downstream, we'll find that the plate has more and more influence on the velocity profile. The thickness of the momentum boundary layer increases. We're now about halfway down the length of the plate. As we continue down to the very end of the plate at 1 meter, we'll find that the plate has a very large influence on the velocity profile. So we'll see in this instance the velocity is 99% of the free stream velocity way up at that value of y, and then a more gradual decrease down to a velocity of 0. And what we also see is that the temperature is equal to 100 degrees C at the surface of the plate, and the temperature is equal to T infinity far away from it. At the solid line, recall, this is where the temperature is equal to 1 degree C. Because air has a Prandtl number that's less than 1, about 0.7, we find that the thickness of the thermal boundary layer is a little bit larger than the thickness of the momentum layer. And that's because for air, the Prandtl number is equal to about 0.7. Recall that small Prandtl numbers means that the thickness of the thermal boundary layer will be a great deal larger than the thickness of the momentum boundary layer. The next simulation we'll look at is water, and what's immediately apparent is that the thickness of both the thermal and the momentum boundary layers are quite a bit thinner. And compare the thickness of the momentum boundary layer for water and that for air. Much higher Reynolds number, much thinner momentum boundary layer. Another thing to observe is that the Prandtl number for water is greater than 1. The Prandtl number is 7 as opposed to air, which had a Prandtl number that was less than 1. Compare the relative thicknesses. Here's for water, the momentum boundary layer is thicker than that of the thermal boundary layer, and here it is for air, the momentum boundary layer is thinner than that of the thermal boundary layer. The next simulation is that of mercury. We have a very large Reynolds number in excess of 400,000. Compare the thickness of the momentum boundary layer between mercury and water and air. We'll find that the momentum boundary layer is very thin for mercury. Interestingly, what we'll also observe is the Prandtl number for mercury is so small. It has a very high thermal conductivity and a relatively small kinematic viscosity. If we zoom in on the end of the plate, what we find is that the fluid is being heated up by the plate, but its velocity profile is not being affected. Its velocity profile is not being affected until it's below the momentum boundary layer. So there's a very high diffusion of heat into the fluid, but relatively small impact on the velocity profile. Let's take a look at our last fluid, oil. Oil has a very large Prandtl number, a very large kinematic viscosity, and consequently will have a very small Reynolds number. Immediately apparent is that the thickness of the momentum boundary layer is off the charts. It's much larger than 0.1 meters. And we see that within the velocity profiles as well. There's no region, unless we zoomed out on these charts, where we would ever see the velocity being equal to the free stream velocity. Oil just has that much viscosity. Let's zoom in and compare the effects. Oil, again, is on the top, mercury is on the bottom. Again, what we found for mercury is that the temperature diffused readily into the mercury itself. The thermal conductivity of mercury is really high. It diffused into a region in which the fluid velocity was not even impacted. So it diffused outside of the momentum boundary layer. In contrast, oil has a Prandtl number on the order of 10,000, and what we see is a very large impact on the velocity profile and a relatively small difference in temperature. So the thickness of the thermal boundary layer is small, and the thickness of the momentum boundary layer is gigantic. In fact, if we scale out quite a bit, here I've got a vertical axis of 0.5 meters instead of 0.1, which was the original vertical axis, and you can see just how much larger the momentum boundary layer is than the thermal boundary layer. And finally, here's a hypothetical fluid in which the Prandtl number is equal to 1. And what we observe is that the thickness of the thermal boundary layer is equal to the thickness of the momentum boundary layer. So both boundary layers fall right on top of one another. If we zoom in on the plot, we see that the velocity is equal to 99% of the free stream velocity at the same location in which the temperature is equal to 1 degree C. And that's true along the entire length of our plate.